the subject of the lecture is impulse and momentum. I will discuss the two quantities, impulse and momentum, and some theorems that relate the two and other aspects of the concept of momentum of a moving object. So first let's consider the following situation. A baseball is flying with some initial velocity v0 and is being hit by a baseball bat with some force F. As a result, the baseball is going to fly away with some final velocity Vf. If the force of interaction between the baseball bat and the baseball is measured and plotted in a force versus time graph, the plot will look like something like this. So it turns out that the force with which the baseball bat hits the baseball is not constant at all times. The force changes with time. However, the force could be averaged over time, and then the average force will be constant. So when that averaging is performed, we can assume that the force acting on the baseball is constant. Then I can take the product of this average force and the time over which the force was applied on the baseball. And this product is known as the impulse of that force. So the product of the average force F and the time interval over which the force was applied on the baseball is known as the impulse J of that force. The impulse is a vector quantity and has the same direction as the average force. The units for the impulse are the units of force times the units of time, so that is newtons times seconds. In reality, all forces of interaction between objects are forces that are not constant. They change over the time of interaction. However, they can be always averaged, and for the purposes of our course, we're always going to consider the forces of interaction between objects to be the average forces, so they will always be constant. So let's go back to the example of the baseball bat hitting the baseball. So we now know that during the process of interaction between the baseball and the baseball bat, the force with which the baseball bat hits the baseball has impulse J, which is equal to the product of that average force and the time of interaction. So let's see what happens to the baseball. So if the baseball has mass m, then when it gets hit by the baseball bat, we know that it changes direction of motion and also the velocity changes. So therefore, a specific quantity associated with the motion of the baseball and the mass of the baseball changes. So this quantity can be written as the product of the mass of the baseball and the velocity of the baseball. And I will label this quantity with P initial. And as you can see, that is also a vector quantity. Then, after the interaction with the baseball bat, that quantity, which is the product of mass and velocity of the baseball, will change. And now it will become P final, and that will be equal to the product of the mass of the baseball and the final velocity of the baseball. So, the force with which the baseball bat interacts with the baseball produces this impulse J, and as a result, this new quantity P for the baseball changes. The product of mass and velocity of an object is called the linear momentum of that object, and the linear momentum of an object is a vector quantity and has the same direction as the velocity of the object. The linear momentum is measured in units of kilogram times meter per second. Those are the units of mass times the units of velocity. I want to caution you that when you do problems involving momentum calculations, the mass of the object always must be converted into kilograms, and the velocity always must be converted into meters per second. Only then the momentum will have the correct units and the answer will be correct. So going back to the example with the baseball and the baseball bat, the initial momentum of the baseball changes due to the impulse of this force the force F with which the baseball bat hits the baseball to a different value after the interaction. So there is a change in momentum of the baseball due to the interaction with the baseball bat. That means that there has to be, or there must be, a relationship between that quantity J and the change in momentum. So let's see what that relationship is. The relationship between the impulse of a force and the change in momentum of an object is given by the impulse momentum theorem. When a net force acts on an object, the impulse of this force is equal to the change in momentum of the object. So on the left side here we have the impulse of the average force F. And then on the right side we have the change in momentum, which is equal to the final momentum value minus the initial momentum value. This theorem is very useful in calculation of forces that cannot be measured with any tools or devices, but we have information about the values of the momentum of a moving object at two different moments of time, and therefore we also know the interval of time over which that change in momentum happened. So let's see how this theorem can be applied to solve a simple problem. Here we have an example in which rain comes down with a velocity of negative 15 meters per second and hits the roof of a car. The mass of rain per second that strikes the roof is 0.06 kilograms per second. Assuming that the rain comes to rest upon striking the car, find the average force exerted by the rain on the roof. So this problem is done by applying the impulse momentum theorem, which states that the impulse of the average force F is equal to the change in momentum of the raindrops. So the raindrops start with initial velocity V0 of negative 15 meters per second. They hit the roof of the car and then they immediately stop, so the final velocity is 0 meters per second. Since the final velocity is 0 meters per second, that means that the term that corresponds to the final momentum will be equal to 0. From there, I can rearrange the terms that are left to get an expression for the average force. The average force is equal to minus the mass divided by the time of interaction of the rain times the initial velocity of the rain. We know that the mass per second is equal to 0.06, and so substituting also the velocity, the initial velocity of the raindrops, negative 15 meters per second, gives us that the average force is equal to 0.9 newtons. In the chapter about work and energy, we saw that the work-energy theorem led to a conservation of energy principle. Now the question becomes, is the impulse momentum theorem related to a conservation principle for momentum? And in order to answer this question, let's apply the impulse momentum theorem to the mid-air collision between two objects. So here is my system of two objects, two spheres, a larger sphere with mass m1 and a smaller sphere with mass m2. They are moving on a collision course sphere number 1 with initial velocity v01, sphere number 2 with initial velocity v02. The two spheres collide, and after collision they move away from each other, sphere number 1 with final velocity v final 1, and sphere number 2 with final velocity v final 2. Let's look at the forces that are present in that system of two spheres as they interact with each other, and also before and after they collide. So during collision, the two spheres act on each other with a pair of forces that are equal by magnitude and opposite in direction. The force F12 is the force with which sphere 2 interacts with sphere 1, and F21 is the force with which sphere 1 interacts with sphere 2. That's an internal pair of forces, because those forces are forces that arise due to the interaction, the physical interaction between those two objects of the system. That's why these two forces are the same magnitude but opposite in direction. We also have forces that are not part of the system that also act on those two spheres. And those are the two weights of those spheres, or the gravitational force on each sphere. So for sphere 1, we have m1g. For sphere 2, m2g. When the two spheres collide with each other, the two gravitational forces are still present, and after the spheres move away from each other, after collision, the two gravitational forces are still present. So the two gravitational forces are external forces for the system. They come from the interaction with Earth, which is not part of the system. Now that I know all the forces that are present in this interaction, let's apply the impulse momentum theorem, and let's see what is the result. The impulse momentum theorem states that the average net force times the interval of interaction, or the interval over which the force was applied, is equal to the change in momentum of an object. So let's apply this to each sphere separately. For sphere number 1, when the collision is happening right here, we have the force with which the second sphere interacts with sphere number 1, so that's F12, plus the gravitational force of sphere number 1, so W1. So this is the net force that sphere number 1 experiences. So we multiply that by the interval of interaction between the two spheres, and that's equal to the change in momentum of sphere number 1. For sphere number 2, we have the force of interaction with sphere number 1, F21, and the force, or the weight, W2, of sphere number 2 due to the gravity of Earth. So the net force that sphere number 2 experiences is that sum multiplied by the time interval of interaction between the two spheres is equal to the change in momentum of sphere number 2. Let's combine the two equations. Let's add them together. So the entire system now is a subject of four forces: the weight of the sphere number 1, the weight of sphere number 2, the force with which sphere 2 acts on sphere 1, the force with which sphere 1 acts on sphere 2, that is the net force for the entire system. Multiply this by the time interval of interaction, and then on the other side we have the final momentum of both spheres minus the initial momentum of both spheres. So final momentum and initial momentum of both spheres. So that is the final momentum and the initial momentum of the entire system of particles or objects. Now remember that those two forces, F12 and F21, are equal but opposite in direction. So these two will cancel out. And now we are left only with the two weights of the spheres. And so finally we are left with the following relationship. The net external force times the time interval of interaction is equal to the change in momentum of the system of particles. So the impulse of the net external force is equal to the change in momentum of the system of particles. This is very important. Now, imagine that the net external force is equal to 0. There is no net external force acting on the system. For example, you take your system of particles, let's say 2 molecules, and then you put them in a vessel where you evacuate all the you put in a vessel that is in vacuum, and then you place it somewhere in space where there is no gravitational force due to a planet or a star acting on these 2 molecules. That is a very good approximation of an example where the external forces are equal to 0, in which case the final momentum of the system of 2 molecules will be equal to the initial momentum of the system of 2 molecules. And so this principle here is known as principle of conservation of linear momentum. The principle states that the total linear momentum of an isolated system is constant or conserved. An isolated system is one for which the sum of the average external forces acting on the system is 0. Let's state some other examples of situations where the net external force is 0. For example, we have a system of 2, let's say, blocks that slide across a flat surface. If we ignore the friction between the blocks and the surface, then that system will be essentially a closed system or isolated system, and there will be no external forces acting on the system. However, if there is friction, then we have external forces acting on the system. Now let's look at one example of application of the principle of conservation of linear momentum. So we have 2 people, a man with mass m2 and a woman with mass m1, that are initially at rest, and they are on an ice skating ring, and then they push off each other and they start to move in opposite directions, the woman moving with velocity v final 1 and the man moving with velocity v final 2. If the woman has a mass of 54 kilograms and the man has a mass of 88 kilograms, and the final speed of the woman is positive 2.5 meters per second, what is the recoil velocity of the man? What is v final 2? Well, this is a perfect example of a system of 2 bodies which is isolated, and there are no external forces acting on the 2 bodies. So the motion happens on ice, so therefore the friction can be ignored, very small. So therefore the final momentum of the system of 2 bodies is equal to the initial momentum of that system. The initial momentum of the system is equal to 0 because the 2 are not moving initially. They have initial velocities of 0. The final momentum is equal to the final momentum of the woman plus the final momentum of the man. From here, rearranging the terms, we get an expression for the final velocity of the man, that is minus the mass of the woman times the final velocity of the woman divided by the mass of the man. Substituting the numbers that the problem statement gives us, we get that the final velocity of the man is negative 1.5 meters per second. The minus sign here just indicates that the motion of the man is in direction opposite to what we have selected to be the positive direction. Notice one more thing. Because the man is heavier, his velocity is smaller than that of the woman. the woman is lighter and her velocity is faster than that of the man. But the momentum of each person is equal. Conservation of linear momentum can be applied in situations where objects collide with each other. By the nature of the collisions that the objects undergo, there are two types of collisions. We have elastic and inelastic collisions. An example for elastic collision would be billiard balls colliding with each other, a bowling ball hitting bowling pins, or a perfectly rigid stainless steel or steel sphere hitting a perfectly flat steel surface and bouncing right back off of it. So elastic collision is defined as one in which the total kinetic energy of the system after the collision is equal to the total kinetic energy before the collision. That means that during collision there is no loss of energy. Inelastic collision is one in which the total kinetic energy of the system after a collision is not equal to the total kinetic energy before the collision. If the objects stick together after colliding, the collision is said to be completely inelastic. So here there is an example of inelastic collision. We have a basketball which hits the floor and bounces back up. So before and after collision, the basketball retains its shape. But during collision, the basketball changes shape. So some energy of the kinetic energy that the basketball has before the collision, part of that energy will be used to return the basketball to its original shape. As a result, the basketball now has less energy after collision to move up in the air. Therefore, the basketball will never return to the original position. If you perform the same experiment with a perfectly rigid steel sphere hitting a steel surface in vacuum to avoid generation of sound waves, which are a form of energy, you would see that the initial and final height or the rebound height of the sphere will be essentially the same. So during inelastic collisions, there is a certain degree of deformation of the colliding objects, and then returning to original shape if possible results in loss in energy. Other mechanisms of loss of energy would be generation of sound waves and also heat due to some friction. When we talk about completely inelastic collision, an example of such collision would be throwing a piece of clay at a wall and the piece of clay getting stuck to the wall. So there is deformation, but then there is also the two objects remaining together. Another example of completely inelastic collision would be two train cars colliding with each other and then moving together as one object. That's an example where the kinetic energy before and after collision for the system is not the same. Let's look at the following example and how we can apply conservation of linear momentum in the case of inelastic collision. So a car with mass of 2 kilograms is moving at 10 meters per second to the right. It collides with 4 identical cars connected to each other, and all 5 cars move together to the right. What is the speed of the cars after collision? Is the collision elastic or inelastic? So here is the sketch of the situation before collision and after collision. So before collision we have this one car moving to the right with 10 meters per second initial velocity, and the car has mass of 2 kilograms. The other 4 cars with combined mass of 8 kilograms are stationary, so their initial velocity is 0. After the collision, the mass of the entire system is, the mass of the 5 cars together is 10 kilograms, and we want to find the velocity after collision. To solve this problem, we have to apply conservation of linear momentum principle. So the conservation of linear momentum states that the final momentum of the system must be equal to the initial momentum of the system. The final momentum of the system is calculated as the mass times the final velocity. So that would be the mass of all 5 cars together times the final velocity of the 5 cars as they're moving as one. The initial momentum will be equal to the momentum of the single car, which will be the mass times the initial velocity of the single car, plus the momentum of the 4 cars as they are standing stationary there waiting for that one car to hit them. So that initial momentum of the 4 cars will be the mass of the 4 cars times the initial velocity of the 4 cars. This term is equal to 0 because the cars are not moving initially. From here I can solve for the final velocity, and that is equal to the mass of the single car times the initial velocity of the single car divided by the mass of those 5 cars together. Substituting the numbers gives me a value of 2 meters per second for the final velocity of the 5-car train. So notice that before collision the single car was moving with 10 meters per second, and after collision the entire train of 5 cars is moving with 2 meters per second. So that is 5 times less. But also notice that the mass of the 5-car train is 5 times more compared to the mass of the single car. And so it makes sense that the final velocity is 5 times less because the mass is 5 times more. And the momentum must remain the same. Now to answer the second question, is the collision elastic or inelastic? Let's look at the kinetic energies before and after collision. The kinetic energy before collision is the kinetic energy of the moving car, and that is equal to 100 joules. And then the kinetic energy after collision is equal to the kinetic energy of the 5-car train times the velocity of the 5-car train to the second power divided by 2, so that is 20 joules. So you see that during collision the system lost 80 joules of energy. And so the typical mechanisms of loss would be sound generation. There will be, when the cars are getting stuck to each other, there are some springs there in the, when they collide. And possibly there will be some heat generated during the collision. So, the fact that the two kinetic energies are not equal means that this was inelastic collision. And because the cars got stuck together and started moving as one, that also tells us that this collision was completely inelastic collision. So here is a different example, which is called a ballistic pendulum. A ballistic pendulum is just a wooden block that is hanging from a string, and a bullet is shot into that block, and this device can be used to calculate or determine the initial velocity of the bullet. So here we have a 2.5 kilogram wooden block, and a 0.01 kilogram bullet was shot into it with some initial velocity v01. The bullet is now stuck in the block, and so the block bullet system with the combined mass of the two is swinging up in the air from its starting horizontal position here, and it reaches some height above the starting position. The question is, what's the initial velocity of the bullet? To solve this problem, two principles are used. First, we use conservation of linear momentum, and then use conservation of, and also in parallel to that, use conservation of kinetic energy. Let's first apply conservation of linear momentum. So for the system of bullet and block, the initial momentum must be equal to the final momentum. The initial momentum is the sum of the initial momentum of the bullet and the initial momentum of the block. The final momentum of the system is the final momentum of the bullet plus the final momentum of the block. However, for the initial momentum of the system, we know that the bullet is moving with some velocity and the block is stationary. So therefore, the second term in this sum is equal to 0. That is the initial momentum of the block. We also know that when the bullet gets lodged into the block, that now becomes one object that moves, and it has the mass. It has a mass that is equal to the sum of masses of the bullet and the block. And so this one object is moving with one velocity. So therefore, the momentum of the system after collision is simply equal to the total mass of the system times the final velocity with which the entire system is moving. From here, I can write an expression for the initial velocity of the bullet, and that is equal to the mass of the system times the final velocity of the system divided by the mass of the bullet. So I know everything except for the final velocity of the system. So now, that's where I will apply conservation of energy. So I will apply conservation of energy principles to find the final velocity that I need to calculate the initial velocity of the bullet. So in this example, the final velocity from the calculation with conservation of momentum will be the initial velocity for the kinetic energy term here. I'm going to keep the same notation with the understanding that this final velocity is just the initial velocity for that pendulum motion now. So conservation of energy principle basically tells us that the kinetic energy of the system as it starts to swing up will be equal to the potential energy of the system as it stops moving at this height, hf. So then, writing this explicitly for the bullet and block system, we have the mass of the system times gh final is equal to 1/2 the mass of the system times v final squared, where, one more time, v final is the velocity with which the system starts to swing up here as a pendulum. From here, the masses cancel out, and I get an expression for the final velocity, for this velocity, and that is square root of 2 times gh final. Replacing the numbers in here gives me a value of 3.6 meters per second. Then I can get back to the expression for the initial velocity of the bullet, substitute all the values in there, and calculate the result, and that is that the initial velocity of the bullet was 896 meters per second. So those types of problems where an object is shot towards another object and both get stuck, and then they swing together as a pendulum, is always done by using conservation of linear momentum and conservation of energy. The examples that I discussed so far were all examples of one-dimensional interaction, one-dimensional collisions. However, in general, collisions are in 2 or even 3 dimensions. So let's look at, at two-dimensional collision conceptually without actually going into concrete examples, just to explain how the principle of conservation of linear momentum is used. So here we have 2 spheres with masses m1 and m2 moving with initial velocities v01 and v02 on a collision course as shown. They collide, and then after that they move away from each other with some final velocities v final 1 and v final 2 as shown as well. To be able to calculate any of the velocities that are shown here, we need to use conservation of linear momentum and possibly also conservation of kinetic energy. So, since this is a two-dimensional problem, that requires that each velocity is presented as the sum of its components, so by components. So, for example, the final velocity of the first sphere components are shown in this small drawing here. That means that the conservation of momentum equation will be written for the x coordinate direction and then also for the y coordinate direction. So for the x coordinate direction, we have that the final momentum of the system of two spheres is equal to the initial momentum of the system of two spheres. So this is final momentum in x direction of sphere number 1. This is the final momentum in x direction of sphere number 2. This here is the initial momentum in x direction of sphere number 1. And this here is the initial momentum in x direction of sphere number 2. And similarly, we have the final momentum of both spheres, of the system of both spheres in y direction. And that's equal to the initial momentum of the system of two spheres in y direction. So we have two equations here that can find us two unknowns. But we also have, so we have four unknowns total, right? We have, let's say if we know the initial velocities of the two spheres, then we have four unknowns for the components of the final velocity. So if we want to find those, we need more equations. So where do these equations come from? They come from conservation of kinetic energy. Remember that depending on the type of collision that these two objects undergo, the kinetic energy is either conserved or not conserved before and after collision. Typically those examples are about elastic collisions, so the kinetic energy before and after would be equal of the entire system. And so that gives us two more equations, one for the x direction and one for the y direction, that can be added to that system of two equations here, and then I can solve for any of the components and then find the final velocities after collision. So these types of problems conceptually are no different than before, but mathematically are more involved because all the components here will involve trigonometry. And so this becomes more of an exercise in math or algebra rather than actually understanding the physics of the problem. However, they describe more accurately what happens in real situations when collisions occur. Now let's look at one more important quantity that is related to the positioning of the particles that comprise a system. So here we have those two spheres that are moving towards colliding with each other. And so the mass distribution of the system here changes as the two approach each other. After collision, they move away. The mass distribution of the system changes again. So it is convenient to introduce a new quantity which is known as, or called, the center of mass of the system, in terms of which we can discuss the evolution of the system before and after collision. So let's look at the following configuration. We have two masses, M1 and M2, that are positioned a distance x1 and x2 from the origin of one-dimensional coordinate system with positive orientation to the right. So then I can calculate the center of mass of this system by taking the sum of products of mass and position for each particle and dividing that sum by the total mass of the system. So this gives me the position of the center of mass with respect to the origin here. So the position of the center of mass is equal to the mass of the first particle times the position of the first particle plus the mass of the second particle times the position of the second particle divided by the sum of the masses of the two particles. Essentially, the center of mass is a point that represents the average location for the total mass of the system. The total mass of the system does not change, but when the particles move around, the mass distribution changes. And so the center of mass represents the average location of the total mass of the system. Now let's look at what happens to the position of the center of mass as the two particles move from their original positions. So the first particle displaces by a distance of delta x1, and the second particle displaces by a distance of delta x2. So then I can calculate the displacement of the center of mass, delta x center of mass, as the product of the mass of the first particle times the displacement of the first particle plus the mass of the second particle times the displacement of the second particle divided by the total mass. From here, if I divide by the period of time it took to displace from the original position of the center of mass to the new position of the center of mass, I can get an expression for the velocity of the center of mass. And so, delta x center of mass divided by delta t will be equal to the mass of the first particle times delta x1 divided by delta t, plus the mass of the second particle times delta x2 divided by delta t, and this sum divided by the total mass of the system. But remember the definition of velocity. Velocity was defined as displacement divided by elapsed time, which means that this term here on the left is simply the velocity of center of mass, and then for the first mass, delta x1 divided by delta t is simply the velocity of the first mass, and for the second mass, delta x2 divided by delta t is simply the velocity v2 of the second mass. Now also remember that in an isolated system the total linear momentum doesn't change. That means that the velocity of the center of mass doesn't change. This quantity is a constant for an isolated system. This knowledge is very useful in solving certain types of problems involving looking at the system of particles as a whole and not as individual particles. This concludes the lecture on impulse and momentum.